The next session is indeed distributed computing. It's a rarely covered topic in quantum computing conferences, so we had the idea that it would be interesting to cover that, because most of the time we think that telecommunication in the quantum space is basically around using quantum entanglement to create a so-called quantum cryptography. But it happens that the telecom applications of entanglement are much broader. And that's what I want to cover with our two friends, Marc Kaplan. Can we see him? Marc Kaplan is the CEO and co-founder with somebody named Elam Kashefi. I don't know who is that woman.
I don't know.
Of VeryCloud. And we won't cover your whole bio, but what I would like to mention is you worked for a while as a researcher in Montreal, and you had the opportunity to work with Gilles Brassard. He's one of the beasts of the BB84 protocol. So again, Hall of Fame connections for all of you guys in all these panels. And we have Valérian Guez is the co-founder and is the CEO of Candela. And previously he was a PhD, and I don't know if it was postdoc as well, but in the team of Pascal Sonlar at C2N in Palaiseau. So it's a team that has been building for a long time very high quality sources of photon qubits. And so you will explain what you do with distributed computing and how do you team up, because you are working together in that dimension. So Marc, we'll start with you. And you have a couple of slides, I think, to show, to describe what you do and what you plan to do. And then Valérian.
Indeed. Do you have the slides, or shall I share them?
Magically, the slides should appear.
If the slide don't show, I don't see any.
We have the slide.
We see one slide. It's your slide, Marc, yes. And it's a high quality one, so it means it's local. Yep.
Indeed.
Okay, you can go ahead.
Second. Yeah, sorry. So at VeryCloud, we are a quantum communication company. We are developing mostly applications for quantum networks, and the foundation of VeryCloud is very much related to this vision that we had, that in the long term, the quantum networks, they will evolve. They are not just about quantum key distribution networks, which are the networks that we have now, but they will evolve in the future, and the way they will evolve is very interesting. So currently, for quantum communication networks, we use, the hardware for QKD, right? But in the future, I mean, the furthest vision that we have about quantum network is a quantum internet. So in a quantum internet, we really think of quantum computers connected together using quantum fiber connections, and distributing entanglement arbitrarily on the network. But of course, this is a very long-term view because, well, in the first place, it requires quantum computers. But on the way between current situation and this end goal, there are multiple steps that are interesting on their own. So we need some hardware for that. For quantum computers, we need single photons, for example. It's one example of technologies that Valérian is working on. We need memories, we need to manage entanglement, and we need to have fault-tolerant computation. And it turns out that each one of these elements unlock new applications. So we don't need to jump from the current situation to directly to a quantum internet, like a full-scale quantum internet. We will add these components to the networks one by one. And as soon as we have one new hardware component in the network, we also get new applications, which is really the interesting story that we're trying to participate to at VeryCloud, by designing these applications and making the quantum networks ready for this new hardware. Sorry. So on the way to this. So the focus that we have on quantum networks is very much centered on applications, as I said. And you can see on this slide here, we identified a number of applications that we have identified as being sort of the most interesting ones. So quantum key distribution is what we can do with the current hardware. Once we know how to send single photons from one place to another, we get end-to-end security using quantum repeaters. But then very interesting things happen when we start having quantum memories and entanglement. In particular, we have identified that one of the big needs in security now is identity management. And this is one thing that we can get using quantum technologies, more secure authentication and identity management. Then using entanglement, we can unlock new kind of applications related to data aggregation and secure classical distributed computation. And the last step, when we get the quantum computers, is this quantum internet. And here we unlock sort of what people like to call the killer app of quantum networks, is secure delegated quantum cloud computing, which means that you can use a very light client. Client is very similar to what we can do with current technology for quantum key distribution. And you can delegate quantum computer, you can delegate a quantum software to a server without revealing the software itself. So it's a very fundamental application. It has a lot of consequences on the management even of these of the quantum computers and the business model behind quantum computing. And this is kind of the end goal for us at VeriCloud. Right. So Valérian, do you want to talk more about the hardware components here needed?
Maybe I can give a word about the role of the photonic platform here, because actually when you mention a quantum network, behind this there is a notion of flying qubits, and photons, as far as I know, is the only particle that can be a perfect flying qubit that will offer the possibility to interconnect devices working with stationary qubits, such as superconducting qubits, ions, atoms. So actually, in Candela, we are trying to develop, and we are doing this successfully. We are developing the hardware to interconnect the devices together and to work with VeriCloud about the implementation of such a network. So one of our main products is single photon sources, solid state single photon sources. This is one building block for such network. In the future, we will develop sources of untangled photons, like N untangled photons or cluster states, and such as we can also implement memories for networks for the storage of quantum information and repeaters.
Okay, you didn't have a slide to show. I wasn't sure. I think you had a slide and we don't see yet, but whatever. One question for you, Mark. Do you think that in the end we're going to have a real quantum distributed computing architecture, meaning quantum computer on one end, quantum computers on the other end, quantum telecommunication in between? And what would be the key, let's say, business or application benefit of this kind of architecture for the strawman? What could you say about that?
Yes, so probably the setup that makes the most sense for distributed computing is what I mentioned earlier, which is this secure delegated computation. It's an application that allows to delegate. You can write your software in your favorite environment and delegate it to the server. So if you think about the current situation, all the people, I guess even the people that we heard today, everybody says that they are building a quantum computer, and when it will be done, they will put it in the cloud. And this is what IBM has done a couple of years ago already. And what happens is that when you write on your program, what you do is that you just send a classical copy of your program to the quantum computer. So IBM has full access to this program and can run it on on their quantum computer, but of course they get a copy of the quantum quantum software that you're writing. And for various reasons, this is really problematic, especially in the field of quantum machine learning. We had an interesting conversation with Jordanis Kirinidis about it a couple of weeks ago, that both in the context of machine learning, both the algorithms and the data are very valuable. And so you can think of three actors here, right? You have the person that owns the data, the person that is developing the hardware, and the person that develops the software. And in the field of classical machine learning, you can at least put all these actors together, or if you are owning the data, you can buy facilities for, you can buy a cluster computer to run your classical machine learning algorithms. But in the quantum world, this is really problematic, and you need to rethink this situation. And by using quantum distributed computing, we get to the situation which is a real quantum cloud infrastructure in which you delegate your computation without revealing it. It's very similar to quantum cryptography, except rather than sending single qubits or rather than sending keys, you send an encrypted program, and then the program is run by the quantum computer.
Okay, and one question that would be the reverse one. In your slide, you talk about secure classical distributed computing. Does it mean that, for example, you would be a vendor of quantum technology to classical cloud vendors like OVH or whoever, Scaleway in France, or maybe Amazon elsewhere? What would be the way you would work with classical cloud vendors?
So, I mean, the way we see it today. So, what we are doing at Very Cloud is, we start from the theoretical work that is produced in academia, and we try to work it out to make real use cases out of them. So, indeed, I mean, the vision that we have is that the quantum computers, when they will be available, there will be a kind of HPC-like facility that will hold this quantum computer, and you would need to connect to this. Each client would need to connect to it. So typically what we do is managing these connections between one central node and clients.
Okay, thanks, Marc. I would like to switch to Valérian. I know that Candela released recently a very nice product called Prometheus. It looks like it's a product that's going to be enabling the production of quality photon qubit in a smaller form factor. How would you relate that work to the discussion we have right now, in the way you can distribute the product, in the way it could be productized or put in place in data centers or whatever user?
Yeah, thank you, Olivier, for giving me the opportunity to present our last project, Prometheus, that we released last September. So actually, you can see one of these behind me getting assembled. The way we have about Prometheus, it's going to be a building block for quantum future, quantum applications. So for example, quantum network. In one rack cabinet, there's all the components that you can find in a lab 3 years ago. I mean, the cryostat for the servers, the lasers, the electronics to control everything, the qubits, and then you can just have one fiber that you can plug on it and connect to your network or to your computing platform, for example. We're also providing these devices to many international actors in optical quantum computing, for example, in Australia, in Russia, in the Netherlands. They use our machines and they use the sources that are inside Prometheus. The advantage is that now it can be installed anywhere, for example, data centers, HPCs, any customer place. So it's gonna be a product that's gonna be installed on premise. And inside, actually, we can customize it a bit. So you can host optical quantum processors. So we have a collaboration with a Dutch startup called QX they fabricate processors, and we can integrate their processor in Prometheus, or you can just use it and plug it to a quantum network. And about this, I have a good news that I would like to share with you. We did not have time to release the news. We have the support from Région Île-de-France for the development of these sources, these devices for telecom applications. So we have some funding to develop the same devices compatible for telecom applications. We are starting to discuss with big firms like, I cannot give too many names, but like Thales, Orange, to implement these devices on the field for quantum networks, for communication networks. So yeah, I hope I answered your question. Just to tell that it was a long development, 3-4 years of development supported by BPI France through iLab, the iLab program. So I would like to thank BPI France and their support for this.
I have one additional question for you about this. What I would like to understand is how this new product is enabling you to scale more. We talk about qubit scalability in the morning. How is this enabling better communication, longer communication, or whatever, on a practical way?
Yeah, this is a very good question. There are two things. One thing is you need to provide good performances to our customers. And what I mean by performance is the brightness. In our terms, this is basically the probability that you will have one photon exactly when you want it. And this is what we call the brightness for a single photon source. This is a bit hilarious, but this is our definition. And this, we have improved the brightness by several orders of magnitude in the last years in collaboration with CNRS and the group of Pascal Senella. And now, by providing a bright source, we can actually increase the range between 2 points when you will need to exchange some quantum keys, for example. Because what limits the distance between two points for quantum key distribution, there are the losses and the efficiency of the sources and the detectors on each point. So about the losses, there is something you cannot change. This is due to the distance. But if you improve the efficiency of the components at the source and at the destination, you can increase the distances easily.
At last, for both of you, if we have the time in 3 minutes, can you elaborate on all the partnerships you have built beyond working together? Because I know you work with some research in Italy, you work with the Dutch, with Quicks. So can you say what you do in that space?
Maybe if you have the second slide.
Yeah, maybe. Yeah, it shows up. Excellent.
We have the answer.
Okay, you can go ahead.
Mark?
Yeah, I can quickly say, I mean, Valérian knows the institution probably better than I do, but I know the content of the work that we're trying to perform together is, as I said, as I mentioned earlier, when you add these new components to your networks, these new hardware components, you unlock new applications, and typically single photon sources such as the one developed at Candela are the first component that we want to add to these to the networks, so the existing networks. So the work that we're performing together right now is to identify what applications would become possible with these clean single photon sources beyond quantum key distribution, of course.
So would you put Quicks somewhere over there and the team from Fabio Carino, or is it something very different? Valérian.
Well, sorry.
Maybe Valérian. It's more Candela partnership.
Sure. Yes. So Very Cloud, Candela, we are both collaborating in the side the Reopen program focusing. Very Cloud is beneficiary of this program, and we are a provider. In this program, we aim to develop an optical quantum platform for boson sampling and hybrid quantum computing. In parallel, we're also collaborating with Very Cloud and other platforms such as Pascal or Orca in the UK to develop quantum computing in a cloud, in a secured cloud that you can access from a network from far.
Okay, I need to stop my favorite to startup right now. We need to close this panel. It was very exciting. Thanks a lot, Olivier, to bringing this new aspect
Thank you.
to the
Thank you.
meeting. We're going
Thank you
to
both of
move
you.
on. Excellent.